Hello everybody, good morning and welcome to this new webinar. For today, we want to have a closer look to 4 different applications, which you can see in the next slide here. Before this webinar, we had a call for applications to have a closer look at, to assist with finding solutions for challenges. But unfortunately, there were no input from your side, so we decided to take some of our applications out of the last 15 to 20 years. So there are enough challenges from the past and success stories. So these 4 we will have a closer look today. The first one is what I call black splitter. Second one was a backplane. Third application was an infrared camera. And last but not least, a sensor with a dynamical usage having special requirements. So the initial situation from the first application, we can see here. This is a very simple design. It's a replacement for a formerly cable harness. It's a stack up with 4 layers in the rigid area, 2 layers in the flexible area. So a well-known stack up for flex rigid technology. And I found this by chance in walk around in the production and was fascinated by the picture I saw. And the point of my interest was this inside the circle. There are some crossings. That means we have 2 layers in the flexible area. The dark lines coming from the upper half of the left connector going down to the smaller one on the bottom side, and there are some bright lines on the top of the flex core going from the lower half of the bigger connector to the upper connector. So there are crossings in the flex area, forcing the stack up to have 2 flexible layers. The other point was that this construction, this shape, needs a lot of area in the production panel. So there's a lot of area lost. So I thought about improvements and contacted the customer, and it was quite easy to make an improvement. This is a solution some weeks later. You can see the functionality is exactly the same. We still have 1 bigger connector on the left side and 2 smaller connectors on the right side. But the big difference you can see at once, there's only 1 clear layer of flex. So there are no crossings in the flex area. And the way to reach this was to have all the crossings in the rigid area. So there we can use wires. We can pre-sort the lines prior to the flex rigid transition, and finally succeeding in reduction of layers in the rigid area from 4 to 2 layers, and in the flexible area from 2 flex layers to just only 1 flexible layer. So this is much more easy to produce as a PCB. The flexible area in this case is covered by a flexible solder mask, which is also easier to produce compared to the lamination of a polyimide cover layer. So it was a small change and had a big impact on the price. So roughly the price is still half of the original situation. The other point, there should be used nesting. So I just drawed one line. So you can also imagine if the Y shape is nested into another, there could be even more improvement in the utilization of the production area. So think about nesting and reduce the needed area. This again saves a lot of money. Let's come to the second application. This was backplane. So again, the task was to replace a cable harness, and this is the construction from the mechanical construction. So you can see different connectors. By the way, the PCB is really huge, 431 millimeter by 300 millimeter, and thickness is 2 millimeter to have enough stability for the connectors and the fitting and unfitting of the connectors. So we've got 14 connectors with 64 pins and 18 connectors with 42 pins. The challenge from the mechanical design was that there was not really a lot of thinking behind that, or let's say in different, it was in a chaotic manner. So the top left connector has to be connected to the bottom right connector, and all the other connectors also with crossing 100%. So ending up in the situation that we really have a lot of connections which are 100% with crossings. So that was a challenge, how to do the stack up and the layout. And the first idea of the designer was this one, this approach you can find in the IPC specification 2223, having 4 layers in the rigid area and having also 4 copper layers in the flexible area to get all the crossings there. But of course, this stack up is very expensive, and so we just thought how to manage this, and the idea to solve this challenge I will show you in the next slide. Solution is simple but very effective. We have to ensure that all the crossings are done in the rigid areas. So there's not very much area around the connectors, but it's enough to place wires there and to pre-sort again all the lines prior to the flex rigid intersection. And then the lines could be placed parallel one by one over the flex area, and thus only have the need of only one copper layer in the flexible area. The question at this point is, what is your target? Normally, if you replace a cable harness, normally there are standard cables, so you don't really need shielding layer or a reference plane in the flexible area. It's enough to have just one copper layer in the flex area. Of course, if you want to replace shielded cable or high frequency cables, special cables, that's also possible with flex rigid, but then you need at least one reference or shielding layer. So then this will be more complicated, but not impossible. We have a lot of applications with shielded constructions, normally 3 layers in the flexible area. So coming back to this application, the final layout looked very proper and simple. So this shows the top layer, which was also the flexible layer in the flexible area. And let's have a closer look to a detail out of this design, the red line shows us the intersection between the rigid area and the flexible area. So in the rigid area, we can see the through holes for the connectors to solder in, and we also can see a lot of wires and the different layers to do the pre-sorting of the lines prior to the flex-rigid intersection. This gave us the chance to succeed in a just 4-layer design, but not having 4 layers in the flexible area, having just 1 copper layer in the flex area. So this is a really cost-effective solution for this challenge, and especially if we think about the size of the PCB, this PCB could be placed 1 time on a production panel. So the cost saving is remarkably. So after the 2 success stories, I want to make another call for more examples and success stories. For sure you have challenges in your daily work regarding flex-rigid designs, maybe regarding material or layer stack up, design issues, creating of delivery panels, maybe cost pressure in the product, so or having special performance requirements. We will be glad to assist you in the solution. So please give us a hint and we will come back to you. As well as we are sure that you have already mastered similar or even greater challenges than I have shown you. And it would be really nice to share this with us. We would like to handle this during a webinar like this one today. So now you have some seconds to give us a hint now in the question window, and we will contact you afterwards to check up what we can do with this. Okay, so you also can contact us with our team address, which is flex@we-online.com. So that's another way to contact us for getting support. Next application is a infrared camera, and here we can see the PCB populated on the top picture and as a bare board within the delivery panel on the bottom of the right side. So we can see that there are some components soldered on flexible parts. That means for the production of the PCB that we need a special way of production. We have to open the polyimide cover layer foil. We also have to apply a solderable surface in these areas, so electroless nickel immersion gold on flexible inner layers, which is not a standard process. So these are all special for the production of the PCB, which make the PCB more expensive. That's not all. Also for the further processing of the PCB in terms of applying the solder paste, the assembly process, the soldering process, and as well the testing process, there is a need for special processes. So you cannot handle this in your standard lines, production lines. This makes the system completely more expensive, not only the PCB, but as well the complete process. Thinking about that challenge, we can solve that again very easily. The way for this is to put components always on rigid parts. So the termination of the flexible tails should be rigid again. So now this is a standard PCB. We don't have a need of wires in the flex area. We don't need openings in the polyimide cover lay film. We don't need application of any solder surface on flexible areas. So this makes the PCB around about 30% cheaper. And as well for the following processes: solder paste printing, assembly process, soldering, and testing finally. All for the cost savings alone for the PCB is round about 30%. So now let's have a look at the next and last application. This is a special application, as the application is a dynamical bending application. On the left side you can see model of how the shape of the PCB was, and the small green part, rigid part on top, is the location of the sensor. And this sensor was mounted, as you can see on the picture, making a movement in Z-axis. The stack up of the application was a 4-layer construction with 2 flexible layers inside. So far, so good. So that's a well-known standard again in flex rigid technology and stack up. But the problem was that after around about 500,000 of bendings, the customer got cracks in the flexible area, right in the area of the flex rigid intersection. So this was tested by using a turning roll and applying a amplitude of around about 1 millimeter to the sensor area. After checking this application and making some tests by hand, we could see that the flexible area was really stiff, so it was not flexible enough, forcing the flex right at the flex rigid intersection, having stress there, leading to cracks in the copper. Some actions to reinforce this area, you can see right in the red circle in the picture, they were not successful. So still there were problems after around about 500,000 bendings, and the target was just double of this. So what is the solution for this application? One part of the solution was the change in the stack up. So still we have 4 layers in the rigid area, but we reduced the flexible area to just 1 copper layer. That was possible to have all the lines on just 1 layer, and the result was in a reduction of the thickness and thus significantly thinner and flexible, more flexible. At the same time, the cost of the PCB could be reduced by around about 40%, as the production of a 1-layer flex outside is much more easy compared to a flex inside, and also the material is cheaper. So this was one part of the solution, but the other part was a change in the mechanical design. So the stiffness could be really reduced by making the flexible part longer. So we had to just move some of the components away from the middle of the bigger rigid PCB, and thus we could enlarge the flexible length, making it much more flexible. So the result was better and cheaper. The requalification test was terminated after more than 2 million bending cycles, so the target was reached and even overfilled by more than 100%. And after the complete testing, all of the contacts were still okay. So no cracks in copper, and this was a high volume application, and there are no problems in the field. By the way, we did not just test one change or one improvement approach in the mechanical design. After the discussion with the engineers, we tested different variants: flex inside, flex outside, even having a even longer flexible tail and folding that, folding that around the rigid part, just to try several approaches. And the best and cheapest solution was that on the left bottom side, which was then finalized and tested finally. So all the applications with dynamical bending have to be qualified and tested in a final application to be sure that they are working. So this was a really interesting and smooth, successful solution. And this was the last application I wanted to show you. So that's the question: how can we support you in your challenges and in your daily work? And now, thank you very much for your time and your attention.